Okay, so what I'm going to want to do today is at least present you one technique which also belongs to the framework of error minimization in context of graph-based SLAM. In context to the approach presented so far, the technique presented here doesn't rely on the Gauss-Newton approach, but uses a gradient descent-like method in order to try to find the minimum error configuration in a post graph. So this is a technique which actually became popular in 2006, 2007, around that time, trying to find, quite effectively try to find minimum error configurations, especially in the context of bad initial guesses. So the Gauss-Newton typically converges faster than these methods over here. Like Gauss-Newton requires, for example, that your Jacobian has full rank, and it's sometimes less robust in the context of bad initial guesses in terms of local minima. And these gradient descent methods have the potential to be a little bit more robust in this context. They don't have to be, so still the same issues that you have may show up here, but it turned out that it's quite often a good idea to use such a method actually for initializing your Gauss-Newton. So if you are in situations or if you're confronted with problems, optimization problems that often run into local minima, which are very bad initial guesses, it may be a good idea just to use a few steps of a gradient descent-based approach as a pre-processing step, and then continue with your Gauss-Newton. So it's kind of strongly related to the Lindenberg-Marquardt approach, really, the combination of the Gauss-Newton step and an additional step where you added this lambda times the identity matrix, which is also related to gradient descent-based methods. So it's kind of a combination of these both. And this presents one work which was especially designed to deal with bad initial guesses and uses gradient descent-based approach. And the key everything was motivated by a variant of gradient descent, so-called stochastic gradient descent. The stochastic gradient descent works in a way that it, so tailored to our problem here, it just randomly picks a constraint out of my set of constraints and then looks at what do I need to do in order to minimize the error which is introduced by this constraint. So only by this constraint, ignoring all the others. And typically, you have a couple of nodes which connect those two constraints. So either these two constraints, you just move those nodes closer together. Let's say if the constraint says these nodes should be the same, they are right now in this configuration, you kind of move them towards each other, and you minimize the error introduced by this constraint. The problem if you approach a problem like this is that you may introduce large errors in other parts of your graph. And so what the stochastic gradient descent-based approach does, it kind of decomposes the overall problem into a number of small problems, and these small problems are given by individual constraints or subsets of the graph that you try to optimize locally, and then fuse all the different solutions together. Of course, the problem is that these different solutions are maybe contradictory. So one constraint says, hey, this node should be over there, the other one says it should be over there. So it can happen that it jumps forth and back. And therefore, in order to kind of merge those constraints together, what the approach typically does, it has a so-called learning rate that linearly scales the update, and this is a function which decreases by, for example, 1 divided by n, so the update gets smaller and smaller and smaller. So it jumps a little bit, but in the end, hopefully converges to an equilibrium point. And so you can just illustrate it like this. So you have, let's say, a small number of 5 nodes over here, with constraints connecting each other. And so you say, okay, this is a constraint I select right now, and this constraint there, these two nodes should actually line up with each other. So what the approach does, it takes this constraint and then tries to compute which nodes should I update to minimize the error introduced by this constraint. So one way would be just simply move this one over here. But this constraint I also this depends on these other nearby nodes, and a subset of the nodes, I also take those into account. This simply depends on how you parameterize your graph in this case. So just to illustrate how the approach works, it randomly selects a constraint, and then it updates the nodes or subset of the nodes based on these constraints, and move them close together, for example, like this one. So it moves these two nodes closer together. And then it repeats this process, setting a new constraint, does the update, and continues forward. So that in the end, after you iterate that, you hopefully end up with a configuration which is your goal configuration. So that's just one way of performing error minimization. So you take out a subproblem, you say, what do I need to do to fix this small, quite potentially easy to solve subproblem? You fix it, you put it back, merge it back into your problem. Of course, the problem, as I said before, may result if you're in configurations where the different solutions actually contradict each other. One says, hey, the node should move to the right, the other one to the right, and the other one says, the node should move to the left, and you need to kind of find an equilibrium point, which is typically done by your learning. And so so-called preconditioned stochastic gradient descent tries to update problems in a way so that the main update rule is written like this. So let's just be the current solution or the new solution I want to have, which starts with the previous solution and adds a delta x to that. And you can actually read that quite nicely if you look at it from the right to the left hand side. So what you see here, Rij is sort of the residual. It's a negative error vector. So it means if you move in the direction of the residual, you decrease the error. So everything you want to do, if you want to update a small subset of these of the error reduced by a subset of these nodes, so select, let's say, 4 or 5 nodes. The thing is, you want to move a node towards in the direction of the residual because this will decrease its error. So you move in the direction of the residual. That's the first thing you do. The second thing you do is you have the information matrix of this constraint over here. This kind of scales the update. How certain are you? The more certain you are, the stronger the update. The less certain, the less information you have, the smaller the update. Okay. Then you have the Jacobian, which kind of maps the update into the space X here, which can be seen as, or it can be a mapping between, for example, the poses and the parameters, because we'll come to that in a second, that depending how you parameterize your graph or your nodes, so if you just store poses, or you represent the poses in a different way, it can have a strong impact on how fast the approach converges here. And something, this gives you the mapping between that. Then you have the Hessian or the inverted Hessian here, which is a preconditional matrix which kind of represents the shape of your error function. And you have this term lambda over here, which is a so-called learning rate. This value starts at, for example, 1. It decreases with the number of iterations. And kind of it linearly scales the update on, so the bigger the lambda is, the bigger the update, and if it goes towards 0, the constraint hopefully meet an equilibrium point, or reaches an equilibrium if this is 0, because then there's no update anymore, and you hope that this is actually the minimum of your problem. So it's kind of a typical gradient descent-based method where you try to follow the gradient of your error function and hopefully end up in the right local minimum. What dramatically impacts how efficient this approach is the way you parameterize your nodes. And just illustrate that. So if you have a set of nodes over here, and say we just have a chain of nodes, and let's say you update those two, you want to update this constraint over here, which connect those two. Or let's say you take this one, which is connected somewhere else, and you, so here's another one. Easier to understand. Okay. And let's say this node, this constraint says, hey, this node should be really close to this node over here. So if only these two nodes are involved in the update, it would result in a graph that this node moves over here. So let's say this moves over here. But if you don't update those nodes, this would be the new constraints you have. This would vanish. The problem is then you introduce a really huge error over here. So the next thing would be you move these guys. Then you introduce a really big error here, you would move these guys. So you need a lot of iterations in order to do all the update. So it may be better to represent the pose of a node relative to some other node. So if these nodes would be parameterized as relative to the location of this node, and these relative to the location of this node. By moving this node, you would move the whole graph. You would directly come up with this solution. So depending on how you parameterize your graph, one update may just kind of move the whole graph as a rigid body transformation, or it may screw up a lot of constraints you have. So depending on how you parameterize your nodes, this can have a strong impact on how fast your approach converges. This is especially important here because we just handle one constraint at a time, and by optimizing or reducing the error introduced by one constraint, I may introduce large errors for all the other constraints. And so I typically have the so-called the poses. This is kind of my x, y, v, yaw, pitch, roll, or whatever I use, what we used so far. And I have a mapping function which maps this into so-called parameters x. These parameters can be, g can be the identity, then I just use, as we used it so far, the x, y, v, yaw, pitch, roll, or x, y, theta for representing our nodes. But it can also be the case that this is simply a different parameterization, so that I simply express the pose of a node in a different way. And the key idea, what you can do, especially in this context of this stochastic gradient descent, is let's choose this function g in a smart way that simplifies our problem. So if we then look into the error minimization, I simply have this e prime over here, which can read as the kind of transformed error. So this is the error now in parameter space. And if I design it in a nice way, this is this mapping G between the poses and the parameters, I can exploit some of the properties that if I move one node, the whole graph moves with that, jointly with that node. Of course, this doesn't hold for all nodes, because if I move the graph back, the update may not be that easy, because I need to commit on one parameterization. For example, which node is represented relative to which other node. Of course, I need to have a unique parameterization. So the first parameterization proposed by Edwin Olsen in 2006 was to use parameterization which is relative to the nodes along the trajectory. So it just says the node, the pose pi is simply the parameter of the node pi is kind of the difference between pi and pi minus 1. So the ith node is parameterized as the difference between the node I minus 1 and I. So if you move, in this case, the node the parameters of xi minus 1, which corresponds to pi minus 1, and you move it, you will automatically move the whole chain of nodes in the same movement. So if you move one node, everything which was recorded after that, you correct in the same way. The problem with this parameterization, however, if you have a very, very long trajectory, you do one update, you need to propagate an update through all the nodes in that graph. So if you, for example, you close a big loop, roll it on trajectory, and this is here 100 kilometers. Really department. It now comes back and closes here a loop with this node. So we introduce potentially a high error, and if you update this constraint over here, this will lead to an update of this whole super long trajectory that we're updating. So one of those updates, this update over here, would involve all the nodes along the trajectory. Of course, you need to update the node, so if there's a huge error somewhere over here, you need to correct it at some point, that's clear. But the problem is that this involves potentially a large number of nodes where there's maybe no big error. So for example, if you were driving around and then you're mapping in an area here very often, drive around 100 times in this area, you know quite well how this environment here looks like because you've accumulated a lot of data. And maybe you just connect this node over here, and if you do the update, you don't need to propagate the error through all this area where you're already really certain about, but you may want to distribute it about in this part of the environment. Only because this is the environment where you're uncertain, the part of the environment where you're uncertain. So that's one of the problems that you encounter with using this incremental parameterization. So what you could do is you can first check what are alternative parameterizations. Or can I do that actually in a better way? And So the key idea you could exploit here is that you try to incorporate the topology of the environment. So if you have multiple loops, and it's exactly the example I've plotted here, if you close here multiple loops, you're quite certain about this part of the environment, it's quite likely that it's good to kind of move this as a rigid body constraint and distribute the error along the other nodes. Any question? No? Okay. So the key idea you want to have is that kind of individual loops should be treated as individual problems, not affecting all the rest, or with little effect as possible on the rest of the nodes. So if I, let's say, have a small environment, where the robot started at 1, moved to 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, back to 1, you have constraints in this way according to the arrows. So 1 has an impact on 2, so 3, there's all relative transformations. And here 7 observed 3, so they are, let's say, assume that they were at the same position, then moves further, and then 9 and 1 again. So if you introduce arrows over here, one way would be to distribute the arrow along the whole, enclosing this loop around the whole trajectory here. But it may be smarter to do that and say, hey, this should be kind of one subproblem, this loop, and this is one subproblem. Of course, they are connected, but if I make a big arrow somewhere over here, it more or less affects only this loop and shouldn't affect this loop over here unless I made a big arrow over there. So the way is, can we actually transform that into, or find a parametrization which supports to kind of decouple those problems and do it, at least to some degree. So that a correction of an error over here doesn't screw up our solution down here, and so forth. We can actually do that by building a spanning tree from that graph. So this can be the spanning tree, which provides a tree structure, what's called spanning tree, which involves all nodes, and all these nodes are connected, but I don't have any loops anymore in the graph. It doesn't necessarily need to be the minimum spanning tree, but just a spanning tree is fine. So this is an example for a spanning tree. So these grayish arrows over here are the arrows I need to add in order to come up with this graph structure, but which are not stored in the spanning tree. So the spanning tree only consists of those black arrows. And the idea of this spanning tree is just to not to replace the graph by that tree, but just to find a good parametrization in which the nodes are represented. And I can now use the tree and I say every node in that tree is parameterized relative to its parent in the tree. So I start with x1, which stores its closest node. Then I say, okay, I simply store where is 9 relative to 1. Where's 2 relative to 1? Where's 3 relative to 2? 4, I say, where's 4 relative to 3, and where's 7 relative to 3? 8 relative to 7, 5 relative to 4, and 6 relative to 5. So for the parameterization, I don't need these constraints over here. I just use this node to find a good parameterization so that the minimum number of updates are involved when I close the loop. And this is done in the following way. When I, for example, close this loop from 8 to 9, over here, then it should only update those nodes which are evolved along the trajectory in the tree to go from 9 to 8 or from 8 to 9 is equivalent. So if I close this loop, it should actually update those nodes over here because these are the nodes which are involved in this loop. So if I look to between 9 and 8, close the loop, I need to update the nodes 9, 1, 2, 3, 7, 8. 1, 2, 3, 7, 8, 9. So this is exactly these bunch of nodes. If I close the other loop from 6 to 7, this involves these nodes over here. So 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Perfect. That's exactly what I want to have. So what this approach provides me is kind of a parameterization so that an update of a constraint only affects a limited number of nodes, and these nodes should kind of correspond to the topology of the scene. At least approximately. Of course, it's not always the case. You can build arbitrary many connections between those nodes. I still need to break it up into a tree, but I want to minimize the effect that I need to update all nodes because of just optimize, let's say, do a small update hopefully. Okay, so I can actually exactly use this tree to do a relative parameterization of the node. So the parameter stored in xi is the pose of the invert. So the p is this vector to transformation of my state space xi as we used before. So x is always the parameter we optimize. So far, x was always the real x, y, theta location. Now here, x are parameters, and the p is the pose. So, and this is just, this means that pi is always parameterized relative to its parent as a relative transformation. So, if I want to store the parameters here in xi, I simply say, this is the pose of this node plus the relative transformation node. This is how I parameterize this node. As a result, if I move this node somewhere else, all the parts move consistently. So I don't know how to compute the parameters of all nodes. Operation over here. I still need to be able to compute the error because it's something I need in my optimization. So let's say if it's rather clear how I compute the error between two nodes, which is simply I compute this value here and compare this to what I've observed. This is the relative transformation between those two. Very trivial. The thing which needs a little bit more investigation is how to compute the error for a constraint that connects two nodes in the graph which are not directly connected with each other. What one needs to do in order to compute this error, we need to go up the tree until we find a node which is parent to pi and pj. So we can walk up here and walk up here until we meet. And then I can ignore the rest of the tree which is above here because I just need to compute the relative transformation between pi and pj need to compare to my observation. So in order to compute the error, I have what my observation here, delta, told me. We should replace it by a big Z, sorry about that. And then I need to go up the chain and down the chain in order to find the transformation between pi and pj. So the important thing, the take-home message from that slide is, even with this parameterization, which is done relatively to other nodes, in order to compute the error, I don't need to walk through my whole graph. I need to just walk up my parameterization tree until I found a common predecessor in this tree. So a common parent. And that's it. So I don't need to draw the whole tree. Okay. So as a result of the if I perform the stochastic gradient descent with this tree parameterization, is that I randomly pick a constraint and then I optimize it. There are two different situations I need to distinguish. The first one is the two nodes are in the tree and are connected by the tree already. So these two guys over here, and I make an update. This means, so let's say the transformation stays here. These nodes should be closer together. The only thing I do, I just move up this node in space so that this constraint is satisfied and no other update of the tree is needed. And everything which sits below that node in the tree is automatically updated given this relative parameterization. This is the kind of what we call open loop constraints on the tree. The other thing is constraints that are not stored in the tree. These are these constraints or off-tree constraints which connect two nodes which are not stored in the tree. And then I need to parse up the tree until I find the common predecessor and then walk down the tree to a different edge again in order to compute the error. And then I update all those nodes involved in this chain and then proceed with that. So I have a small animation which shows how this works. So assume this is the structure we have right now of nodes. And if I, let's say, compute the spanning tree may look like this. This is kind of the tree structure I obtain. And the red one are nodes on the tree, and the grayish ones here are nodes which are not stored in the tree. These are these off-tree constraints, these loop closures. And what you see here is now how this optimization works. So in the first run of the optimization, it shows all the one constraints optimized after the other. So red and blue always means on-tree or off-tree constraint. So most of them are short. And then so one iteration was shown by optimizing every constraint individually. Just replay that. And then every frame is just one full optimization. So this is one optimization. Inside the optimization, we have single constraints picked and optimized. So red are the picked constraint and blue are those which are updated. And And then kind of after that, just otherwise the video would be too slow. The whole update is shown. That's the key idea how that works. And this works quite well in 2D. So 2D, this is one nice way for correcting those post graphs, especially if you have bad initial guesses. So typically, if you look at the conversion speed of these approaches, how fast approach they deliver the minimum, you can see that these gradient descent based measures are very quick in the beginning, reduce the error, but then it takes very long until they converge to the minimum. And Gaussian approaches are faster in conversion speed with this respect. But they are typically a little bit less sensitive to the bad initial guess. So you can use this as a start point, perform a few iterations, and then, for example, continue with the Gaussian approach. The problem with this approach, however, comes if we move toward 3D environments. And one of the reasons for that is that 3D rotations, as already the rotations in 2D, of course, non-linear, and especially these rotations are not commutative as well. So you have 3 rotation angles, and this can actually screw up these incremental updates here of this gradient descent base quite badly. So the problem is this non-linearity, they're not commutative, the rotations that can actually lead to updates which actually screw up my rotations. So one of the ideas to improve that is say, let's look what this stochastic gradient descent update rule in every step actually means and try to improve that and to better take into account the problems I have in the rotations. So I want to move away from exactly this update rule and find a better update rule which takes into account the properties in the 3D rotations. So, and what this approach actually does, or this update rule intuitively does, it distributes a fraction of the residuals. So this was the residuals at scale, this learning rate, the mapping between the parameters. So it distributes a fraction of the residual in order to reduce the error in one of those subproblems. So all nodes which are used along that tree are updated, and if I move one node a little bit, all nodes along that tree, along the path between those nodes should update a little bit so that the overall error is minimized. It's kind of the key idea of this update rule. The question is, can I do that actually better, taking into account the specific properties of the 3D rotations? That's kind of the key idea of the next step. So I want to come up with an alternative update rule, which still is kind of doesn't use exactly the math of the stochastic gradient descent, but uses the same idea, as it works in the same spirit, but especially takes into account that we have 3D rotations and it's kind of a better knowledge on how to deal with these 3D rotations. In order to do that, I would like to kind of split up the problem into 2 parts. The first is just a correction of the rotational components, so I want to more or less uniformly distribute the rotational error between nodes, and then the translational one. So for example, you have, this is here a chain of robot poses, pi, pj, and I have a constraint which connects these 3. This constraint says, hey, pj should actually be here. So this guy should be over here, and the error along these nodes should be distributed accordingly. I can split that up into 2 separate parts. The first, the rotational update, and then the translational update. So the rotational update would look like that here the orb is still looking straight, and in the post pj should be corrected so that it corresponds to this orientation I have in here. So that means, in this situation here, all orbs were looking straight to the top. I need to rotate all of them a little bit to the left. Let's say I have 5 nodes over here, I have an error of 10 degrees, and kind of, for example, 2 degrees per node. It's kind of easy to do in 2D, because it's just one angle. It's more complicated to do that in 3D because these angles are not commutative and I need to take that into account. Once I have that solution, the translation errors can simply be obtained by just scaling the translation, because the linear function just can scale that so that this node in the end ends up here. So let's have a look to this first step, because this is kind of the more complicated step in here. How do I compute the update for all those nodes which are involved in the update, so that the final rotation here corresponds to the rotation that what my constraint tells me, potentially multiplied with the learning rate, so up to a certain degree. So what do we have? we have relative rotations between nodes R1, R2, R3, Rn, and then I have what the information which comes from the constraint. This is what's called B. So these are the relative rotations along the path. So what's the rotation from R1 to R2, from R2 to R3, from R3 to R4, and so on. And the end I have a rotation. They say this last node should actually be rotated where this one is looking. This is the kind of rotation B. Is it clear what these R's are? What is this matrix R, R1?
The amount of we have to rotate to apply the error.
So far we're not in the error, it's just the relative rotation between the two posts. So R, always the relative rotations. And this guy over here is a fraction of the, so about the correction in the local frame. So where this guy, the transformation from where this guy is currently looking to where it should be looking, given the constraint. Also, it's a relative transformation, the relative coordinate frame. So we want to transform that so that Rn ends up to be here, that red node, or close to that red node, and we have a rotation, a fixed rotation along all those nodes. So we want to compute from R1 to Rn plus B, Rn prime to Rn prime, which corresponds to the corrected rotations. So this is the equation we want to solve. And we want to have all the individual variables R prime. We want to compute, and we have those. So we have that. We want to obtain these ones. So how do I distribute the rotational error along a chain of nodes? Okay? So kind of clear what we're doing. Good. Okay. So let's first assume that the first node is the center of the reference frame. Let's just simplify some of the computations here, but can be easily generalized. So what we want to do, if we want to distribute an error around, so that the final rotation of the last node, Rn, sits at the rotation plus, or multiplied with the rotation B, is we want to compute a single axis of rotation in the global reference frame, and then a fraction by how much we should rotate those individual nodes. The problem I have in 3D, I have not, as in 2D, just one rotation axis, which is the z-axis in the two-dimensional case. I have rotation about the x-axis, the y-axis, and the z-axis. And if I distribute the error over the individual rotations of the individual axis, and they are not commutative, I may end up in completely odd situations. So if I say, oh, I rotate a little bit around the x-axis, a little bit around y, a little bit around z, I end up having a different rotation than if I just do one rotation around x, one rotation around y, one rotation around that axis. As they're not commutative, I cannot simply split the rotation up. Let's say I have a 10-degree rotation around each axis. I cannot split it up into 10 1-degree rotations around each axis and rotate them individually because they're not commutative. So therefore, what I want to do, I want to compute the rotation around a single axis, because if I have a single axis, then I can actually split up the rotations. Let's say I have one axis around 10 degree, need to distribute it over 5 nodes. It would be a 2-degree rotation around this special axis, which somehow lies in the 3D space. Okay, so what I want to do is I want to compute Rn prime. So this is A is in the global reference frame always. R was in the relative reference frame, and A is in the global reference frame. So when I get a new rotation for the last node, which is the global rotation I had before plus the relative rotation which comes from the constraint. Is that clear? Is this equation clear? If not, tell me now. I'll explain it again. It's central. We will need it next slide.
Repeat it again.
Okay. An is the rotation of the node n in the global reference frame. According to the update, I need to multiply it with the rotation matrix B in order to get the update where it should be in the end. And the prime variable is the variable I want to compute. So I want to compute the global orientation of the last node in the global reference frame. Right?
Only the last node, not the...
I will need the intermediate ones as well, but let's start with the last one. Of course, this one I know, and it's a recursive equation we will write now and start with. So this is the global rotation I want to compute. I have the current state, and I have my update by which this should be updated. I also said I want to express this as a rotation around one axis in the global reference frame by a rotation around one single axis. Right? This is because we want to distribute the error, what I explained before. So I can express this as a rotation matrix multiplied by that side. So I can express this as a rotation matrix Q times AN. They should end up with the same rotation, but if I write it from that side, you can read that as a rotation in the global reference frame. Because this is a relative orientation, which first, if you would multiply a vector from that side, it would be first rotated around B and then rotated around A in the global reference frame. And here it would be first in the global reference frame, and this is kind of turning the whole thing. It's the reason why you can multiply that here from the left-hand side. Okay, so I have that Q over here, and that's the thing I'm interested in. This is a single rotation in the global reference frame around one single axis. And now I want to split up this Q into a sequence of small rotations and then distribute that around the individual nodes on the chain. And as this happens in the global coordinates, it's completely fine. I can just rotate all of them around one axis. Distribute the error around this axis. So I want to be able to decompose Q into a sequence of small rotations. Let's say this is a 10-degree rotation around this axis. This could be seen as 10 1-degree rotations around this axis. Okay, the problem is how do I distribute that error? And there's actually one technique which originally comes from computer graphics, which is called SLURP. You may have heard that already, spherical linear interpolation for angles. And this was first designed in when creating animation movies, and you have an object which moves with a constant speed on a circular arc. You have a very, very similar problem that you need to compute the angles where this object is in the global reference frame so that it gives you a motion with a constant speed. In this rotation, it's easy if this is involves just one rotation axis. Say if you're on that, just need to provide linear, the angles linear fragmented. So if you have 10-degree rotation around a fixed axis, and you want to generate 10 frames, it's just 1 degree, 2 degrees, 3 degrees, 4 degrees, all fine. If it's an axis which is somehow different in space, and you have your pitch and roll angles, it's quite unclear how you need to rotate that. You need to compute this single axis of rotation, and then you can interpolate on that axis. And that's what the SLURP basically does. The SLURP is defined the following way. If you have a rotation matrix R, and a real number between 0 and 1, called U over here, it's a spherical linear interpolation so that you obtain a new rotation R. And if this value is 0, you have no rotation. If it's U, you get the rotation R from the magnitude. But the axis stays exactly the same. So the axis of R prime is exactly the axis of the rotation, of the original rotation. So you maintain the axis, but the angle of R prime is U times the angle of R. So you can move these. So this is kind of the amount by which you linearly split up this rotation angle. So if you have a 10-degree rotation around one axis, and you select those values as the value U as 0.1, you will get the first tenth of the rotation. This is always easy if it's just one rotation axis. It's not easy if you have multiple rotation axes, and that's the way to compute that. So are the properties of the SLURP clear? What the SLURP does. So the SLURP function has an input of rotation and a value between 0 and 1, produces a new rotation. And this new rotation has the following properties. First, the axis of the rotation is maintained. So the axis doesn't change. Just the angle, the amount of the rotation around that axis is changed. And this is changed between R and R prime in a way that is the factor U times the original rotation, the angle around that axis, is the rotation you rotate around R. So if you're in 1D, that's trivial, because in 1D you just have all rotations rotate around the same axis, so you can just linearly interpolate between the angles. So if it's a 10-degree rotation, you multiply it with 0.2, you get a 2-degree rotation. It's trivial. In general, in 3D, that's the way to do that, because if you want to interpolate between those angles, because the angles are not commutative. So you cannot just simply split up a 10% roll, 10% yaw, 10% pitch. It simply doesn't work because the angles are not commutative. Okay. Given that, so given this QK, we can actually obtain the global rotation of a node K. So K prime is Q1 to QK, so all the individual rotations carried out. There's error. That should be AK. Because so here should be an AK, which is missing. Because you're rotating the global reference frame of AK by 1/k of the rotation of Q. And you also know that the relative rotation between RK minus 1 and RK is the global rotation transposed, so the inverse time the original one. So this is a global frame, this is a relative frame. So if I want to say how do I rotate from RK minus 1 to RK, from the node K minus 1 to the node K, and I have their coordinates in global reference frame, simply inverting that one, multiplying with that one. Here it is easy because it's just a rotation on one axis. If we have these two properties, we can just recursively solve the following equations. We say R1 prime, so this is the update, the new relative update to go from R0 to R1 is Q1 times R1. Because this is just, let's say, one fraction of the update around my new axis for Q to rotate the relative rotation R1. So it's easy, I have it. So I know this one, I know that one, here I am. And now I can use this result to compute R2. Because R2 prime is the global rotation of R1, of A1, R1, times A2. So I have this rotation over here times this rotation over here, the second part. So for the first one, this is equivalent because we said the first node is the center of the reference frame. Therefore, otherwise I would have to do a transformation here, which, if I'm not in the first node is not the reference frame. Therefore, this equation holds. And then is the second part. So if I put the transpose in, this is Q1 transpose, R1 transpose, Q1 transpose times Q1, Q2, R1, R2, which splits up into this one, and actually can eliminate those two rotations of each because they cancel out. This is what happens recursively. So RK prime is R1 to RK minus 1 transposed times my small rotation Q around my axis times the other rotations, and then plus RK. So this is a recursive formula which I then can compute the rotational update along the chain of nodes that I want to update. Again, to remind you, we did that because we were the result of the stochastic gradient descent update rule was unsatisfactory because it wasn't knowing about the relative transformation between those nodes. And we now came up with a new strategy which explicitly says, I know that these are 3D rotation angles. And if I know that, I can provide a better distribution of the rotational components by using this spherical linear interpolation because I know that these are angles, so I get a better distribution of the errors on those nodes. Okay, we are running a little bit over time, so I have to interrupt here, so we'll repeat that probably next time again to bring you all on board. And then finish this chapter next week, otherwise we're running out of time today, I'm sorry for that. Okay, thank you very much. Or are there any questions so far? Sorry. Yes, please. Perfect.
I don't understand the very first step. The R1 prime.
This here?
No, beyond.
This one?
Below. No, below.
This one?
Yeah.
Okay. So I said the Q is a rotation of the global reference frame.
Yeah.
And I said I designed that Q in a way that I can split it up into Q1 to Qn, where these are all a fraction of the rotation around the same axis in the global reference frame. And then I want to compute, and I do that because then I can compute transpose the first rotation by Q1, the second one by Q1, Q2, the third one by Q1 to Q2, Q3. And so this is just the first step of this manipulation. It is a rotation of the global reference frame around the axis given by Q at the first fraction of that. Because the first node, let's say you want to distribute a 10 degree error in the rotational component. The first one you take by 1 degree, the second one by 1 degree, the third one by 1 degree. This works if you have the same axis of rotation. That's exactly what's conducted here. So that's a new relative transformation between two poses, which is the old one plus this rotation of the global reference frame. Okay, any further questions? Okay, so then again, we'll start next week. We'll do this derivation again to bring you all on board, and then we continue with this chapter and then focus on the front end design. Okay, thank you very much.